Okay, can you see the screen? Is the screen visible? Am I audible?
Yes, sir.
Oh, okay, okay. So you can see the screen as well, right?
Yes, sir.
Okay, right. So I was hoping to wait for a bit more time so that more people can join, but I guess I will start. Recording has been also started, so it will be available. By the way, everyone who's registered for the course, I also share the recordings of the lectures. You can just share your email address in the group or message it to me, and I'll add you to the drive folder where all the recordings are available if you want the access to recordings. Right? Okay. So, all right. Taha Zia is also here. Perfect. So we can start now. Last time we started the chapter of pressure, and we talked very generally about pressure, and we're doing an example where the task was to compute the maximum and the minimum pressure, and the idea of the example was to tell you the dependence of pressure with area, right? How does the change in area affect pressure? And we learned that we saw that for a maximum area, we would obtain a minimum pressure because of the inverse relation between pressure and area, right? So keeping the force applied constant, just changing the area can change the pressure that is exerted by this particular force, right? Okay. So the problem that we were doing was we have this rectangular block, and we wanted to figure out if it's placed on a flat surface. It can be placed in two different types, two different ways, horizontally like this, or vertically like this. When it's placed horizontally, it's covering more area. So if it's covering more area, the idea was that it would exert less pressure on the flat surface. While if the object is placed vertically, it is covering less area compared to this one. And hence, if it's covering less area, then it would exert a greater pressure on this flat surface, right? So that was the idea. And we were just going to compute the maximum pressure that can be exerted, and that would be obtained by calculating the minimum area. And the minimum area of this thing would be, because this side has a minimum area, let me use some other color, this green side, this side has the minimum area, right? It covers minimum area, and to find the area of this rectangle, you just multiply this side, which is 10 centimeters, with this side, which is 5 centimeters. So the minimum area would be as simple as 10 centimeters times 5 centimeters, which would be 50 centimeters squared. And then you can convert it into meters, right? And that would be 5.0 into 10 raised to power minus 3 meters squared, right? And now you just plug it into your equation for pressure. You have force by area. Now, if area is minimum, then pressure would be maximum. That's the concept that I was trying to tell you about using this problem. So the force we calculated would be the weight of this entire block, and that was 20 newtons from last lecture. So 20 newtons divided by 5.0 into 10 raised to power minus 3 meters squared. And then just do the math. This would give you a maximum pressure of around 4.0 into 10 raised to power 3 pascals, or you can write it as 4 kilo pascals, right? Now compare it with what we got when we found this thing, the maximum area. We made a mistake in the last lecture. This would be centimeters squared, and so to convert this into meters squared, I would have to multiply it with 10 raised to power minus 2 and its power as well, right? So this would have become in meters as 2.0 into 10 raised to power minus 2 meters squared. And this would have then given you a pressure of, let me just write this, 2 into 10 raised to power minus 2 meters squared. And this will give you a pressure, if you put in the values in your calculator, this would give you a pressure of 1.0 into 10 raised to power minus 3, right? This pressure is very small compared to this pressure. So you can see how much of an effect can the area make, or in this specific problem, how much of an effect on pressure can be made by just the orientation of this block, right? So you can experience this pressure, by the way. It's very simple. If you have a book, try holding a book on your in your palm, right? Try holding it placed flat, and then try holding it placed vertically on your palm. You will feel that in this case the pressure is less, right? You will feel it. And in this case you will feel more pain because the pressure is high. And you can feel that change in pressure as well, right? So anyone has any questions from this problem?
No questions.
All right. So no questions from anyone for the entire problem. This problem we were doing in the last lecture. Okay, no question.
Can you please
All right.
do it
So
again? For some reason, I didn't get some part of it.
yeah, can you please repeat what you're saying?
Sir, I was asking if you could do this again because I just didn't understand some part of it.
Oh, all right. So okay, so you want me to do the entire problem again, or should I just would it work if I explain it using this? Just go over through it.
Explain it using this. Like, I just need to go through a quick overview of the problem and what you
Oh,
did.
all right. Okay, perfect. Okay, so basically the problem at hand was that we have a block, and the block was rectangular geometry, right? And it has some dimensions. This side is 10 centimeters, this one is 20, and this is 5 centimeters, the height of the block. And we were given that this block has a density of this, right? And we want to compute the maximum and the minimum pressure that this type of a block can exert on a flat surface, right? And now the first part of the problem would be to figure out, because if you remember, the pressure is force per unit area. So computing area and force is what we want to do. So if we try to figure out force, then what is the force that this block is exerting on the ground? It would be the weight of the block. And the weight of the block is simply mg, right? And then divided by area for pressure. So to figure out the weight of the block, I need the mass of the block. And the mass of the block can be figured from density, which is given. So density is how mass is distributed per unit volume. So I can just rearrange that for mass, and this gives me density is given as 2.0 grams per centimeter cube, and the volume can be obtained, right? Volume can be obtained because it's a cube. So the volume of a cube is length into width into height. So that's 5 into 10 into 20 centimeters. And this gives you the mass of the block. So the mass of the block is around 2 kilograms. Now, force is very simple. Mass times the acceleration due to gravity, which is the weight of the block, and that's 20 newtons. So here we figured out the force. Now the main thing was to understand what area should I be using, and that would correspond to what pressure am I getting, maximum or minimum. So as soon as I look at this equation, I can immediately tell that for a minimum area, I should get maximum pressure because they're inversely related to each other. So then for a maximum area, I would get minimum pressure. So if I want to find the minimum pressure exerted by this block on this flat surface, I'd use the maximum area. And the maximum area would be the area of either this side or the same side on the bottom, right? And so we would have to simply compute the area of this rectangle. And that would be this side is measured as 20 centimeters and this side is measured as 10 centimeters. So 20 into 10 centimeter squared would be the area, right? So that's 200 centimeters squared. And now we just use this area, which is the maximum area that you can have for this shape, and put it in this equation for pressure. So a maximum area would give you minimum pressure, and the force is the weight of the block, and just do the math and this gives you the pressure. The next part was for when can I have the maximum pressure? And the maximum pressure can be obtained if I orient this block in this way, if I place it like this on the flat surface. Because in this case, the area would be minimum, right? Are you getting it?
I understand.
Yes. Yes.
You're getting it, Hassan. Okay, perfect. So then we computed this area, and this area of this side, this one, would be obtained from here, which is this the side that I shaded in green, right? That is that area, and that is the minimum area that you can have from this cube. That would be simply 10 centimeters into 5 centimeters, which is the height of the block. And so you compute that area over here like this, and then put it back into the equation for pressure. Now minimum area should be giving you a maximum pressure, and you can clearly see that this gives you 4 kilopascals, or 4 into 10 raised to power 3 pascals, which is just 4,000 pascals, right? It is obviously very big compared to this number over here. So these are the two types of pressures we can obtain by simply orienting our object in different ways. And you can feel this difference in pressure by just holding a book in your hand in these two different orientations. If you want to, have a feel for this change in pressure, you can experiment it by holding a book in these two ways in your hand. So that was the problem. Is it clear now for everyone?
Yes, clear.
Yes.
Okay, perfect. So now let's. So the well, we can start the next topic, which is pressure, or sorry, atmospheric pressure, right? So atmospheric pressure, and the name really says it all. But let's try to understand what do we mean by the pressure that comes from the atmosphere, right? So, okay, so you're all familiar with the fact that our planet Earth, it has a layer of the atmosphere around it, right? So if this is Earth, this is its atmosphere. Now, the atmosphere is made up of different types of gases, right? Nitrogen, oxygen, and other various gases. These gases are simply molecules, right? They are simply molecules, and molecules there are atoms, right? So it's essentially, you can say that it's made up of molecules, and you can call them air molecules. Now, these air molecules in the atmosphere, they are not sitting still, they are moving. And in fact, this layer is made up of so many of these molecules that they're constantly hitting each other. The molecules are colliding with each other. So if I draw two of them, so they're constantly hitting each other. And when they do hit each other, they're essentially exerting pressure onto each other, right? And these molecules, if I were because of course the atmosphere is everywhere around us. If you're standing on the surface of the earth, you will feel these atoms, these molecules would be colliding against you as well, which means that these molecules would be exerting pressure on you as well. Now, because the atmosphere is everywhere around us, the pressure is exerted on you from all the sides, like, right, in all the directions. That's why sometimes we use the word the atmospheric pressure is exerted in all the directions. And that's the reason for it, right? Because it is nothing but the air molecules colliding with each other and with us, right? That's that would cause some pressure to be exerted on you, and that pressure is the atmospheric pressure. So is that clear?
Clear.
Do you understand the idea of atmospheric pressure? So it's due to the air molecules which are collide. And that would cause some pressure to be exerted, and that pressure is atmospheric pressure. Now, at sea level, the level at which the sea is, right? At this level, the atmospheric pressure felt is given as 1 atmospheric pressure. So that's how we define our atmospheric pressure, right? So we define our atmospheric pressure at sea level, because we need a reference point, right? We need a reference that from this now we can measure different atmospheric pressures. So at sea level, we reference it to the pressure is 1 atm, and this is known as atmospheric pressure. Now, PRESSURE, right? Okay, so 1 atm is just a unit again, and it's atmospheric pressure, 1 atmospheric pressure. And you can write this in pascals as 1 atm is just saying that you have a pressure of about 1.01 into 10 raised to power 5 pascals, right? Now, you might see another unit for pressure, which is mmHg. And the atmospheric pressure in this unit is 760 mmHg. Now let's try to understand, where does this unit mmHg comes from? Now, it could have been anything, right? But let's first try to decipher the unit itself. The unit mmHg is essentially made up of 2 different things. This is the length, and this is the element in the periodic table. What element is Hg? Can anyone tell me?
I do not know.
It's mercury, right?
Yeah,
Now,
I remember
Hg
now.
it's mercury. Okay, so now it could have been any other liquid as well, but it turns out mercury is the most suitable for measuring these pressure and the changes in pressure, because it adapts easily to the change in pressure. Now, how do we get these units? Where does the units for length, millimeters, this mm is millimeters, where does that come from? So the entire idea comes from how do we measure atmospheric pressure? So how do we measure this? We can do this in one way is to use a tube, right? I'm going to try to draw a tube like this and place it in some container, but upside down. Now fill the container. The container is open, right? So I think I'll leave it like this. Fill the container with mercury, right? And so when you do that, eventually some of it will come here as well. Now, just take this container outside in your normal environment. And by the way, this tube that I have, you can measure, obviously, you can use a scale and measure the height of the liquid in this tube. Now, what I'm doing is I'm taking this setup that I just made. I'll take this out in the environment and put it there. Now, remember, you have to remember that the atmospheric pressure is because Earth has atmosphere. You cannot get rid of it. You will constantly feel the atmospheric pressure, and that atmospheric pressure would be felt by this mercury in here as well, right? So it's feeling the pressure due to atmosphere. Now, this means that this mercury is feeling the atmospheric pressure of 1 atm. What we do is we just measure with that pressure how high can the mercury be in this tube. So we just take this setup outside and we take a scale and we measure this length. It turns out that this length is 760 millimeters, right? Or in inches, it would be 29.9 something inches, right? But let's not care about inches right now. So it would be 760 millimeters in height from the bottom. Now that's where this unit mmHg comes from. And this thing is then defined as 1 atmospheric pressure rise to a height of 760 mm. And then you just add Hg. So it's written together like this. And this entire thing that I constructed, it's now you can just call it something, and we call this thing a barometer, right? So that's the answer on how do I measure the atmospheric pressure. And I hope that now the working principle of a barometer is also clear to everyone. So does everyone understand?
Yes, I understand. It's
Yeah. Right? Okay. So anyone, everyone from the entire class, everyone gets it? Okay, I think there are no questions. All right, so this is then barometer. Now, let's discuss the change in atmospheric pressure with the change in height from the surface of the Earth, right? So how does the atmospheric pressure change with change in height? So you have
teacher.
to keep thinking in terms of,
Sir,
yeah.
in under the water, there's also a pressure of water as well.
Exactly. Yes.
Okay.
Right. So we are going to get into that just right after this. Right. We'll talk about pressure in liquids, where we will talk about the pressure. In fact, that's why you can. There is a certain limit that you can dive into water.
Yes.
After that, as the deeper and deeper you go, it feels like that there is a very heavy weight on top of you, and that's because the pressure has increased so much with the depth. And so there is only a certain limit that you can go dive into water. After that, your body will start collapsing under that
Yes,
pressure,
I
right?
heard that under
Yeah.
very deep, there's the pressure is too high to go.
Yeah, exactly, right. And that's why you cannot go that deep into uh, the water, because the pressure is very high, and your body cannot sustain that high pressure, right? We'll get into that right after this thing, right? So now let's quickly talk how would the pressure change in. So okay, so that's actually a good example when you mention water. Water is also a fluid, while air is also a fluid. So these so for example, if you have air over here and under this you have water, right? So this is the surface of the water. uh, the molecules in air are gas molecules, right? And we know that the molecules of a gas are further apart from each other compared to the molecules of water,
Yes.
right?
Yes.
Now, it would make sense to you if I were to say that, now imagine what, or let me put it this way, let me ask it as a question. What would you think, uh, where should the pressure be higher, in air or in water, and why?
Water, because the molecules are closer together, so more pressure is exerted on you.
Exactly, right? So the molecules, they're so close together and they're colliding with each other as well. They collide with you as well, and there are more number of molecules in a particular area or a volume, and they'll hit you more often, and so the pressure would be higher compared to water. And so as you go deeper and deeper down into water, the molecules are even closer, and they will there would be a lot of molecules on top of you, right? So a lot of molecules, there would be layers of these molecules on top of you, and they would be hitting against your head. And so that's why the pressure in liquids is quite high compared to pressure in air. But let's quickly talk about the pressure in air. So if I were on the surface of the earth, not in water, on the surface of the earth, at higher heights, at we can say higher altitudes. So suppose that you're climbing atop of a mountain, right? So you're getting to higher and higher altitude. Altitude is just height, right? uh, what would you expect in terms of molecules over there? Would there be more molecules or would there be less molecules of air?
Less.
Less molecules, right? Because when you get climbing higher and higher and higher, essentially you're trying to escape the atmosphere of the earth, right?
Yes.
So the atmosphere is made up of molecules, but once you go out the atmosphere, it's just complete vacuum. There is no molecules really over there. And so the density of the air molecules will obviously decrease with higher altitude, right? So the density of air molecules fall apart or decreases. Now, if the density of the air molecules decrease, means that there are less air molecules, so there would be less number of collisions happening with you. That means the pressure would be less because the force now due to these collisions is reduced, right? Is everyone
Yes.
getting it?
Yes, sir,
Clear.
I actually have a question. It's kind of also an example, but
Yeah.
it's kind of a mix of them both. So you
Yeah.
explained how when you go up from air, the water needs, when you go down to water, the atmosphere changes. Well, it's you can also kind of say the same for someone digging underground, no? Because like from the above we have the normal atmosphere, but when you start digging into the ground below, if you've seen in mines, the breathing actually becomes way harder because there's way less.
Exactly, right. So yes, you're correct, right? So once you're digging or going underground, I mean, suppose that somehow you teleport yourself under a very thick layer of surface. This is the surface of the earth, and somehow you just teleport. There is a hole over here and you teleport yourself over here. You would feel an extreme amount of pressure on top of you due to all of these you know layers of surface on top of you. And the deeper you go down, the more pressure you would feel on your head, right? So is that what you were suggesting, Hassan?
Yes, sir, that's exactly what I was suggesting.
Right. So okay, so that's this. And then we can also talk in terms of, okay, so at higher heights, another thing also decreases. There's a quantity that's it's called temperature. And at higher heights, why does temperature decrease?
Because
Can you,
there's less air molecules to absorb the energy.
right? Yeah. So more or less, that's exactly true, because the temperature is associated. In fact, temperature is nothing but the measure of the speed of the air molecules or any molecules. The higher the temperature, it's just saying that the higher their speed is, right?
Yes.
So if I go higher into the atmosphere, the temperature is reduced because the molecules above are very slow, are very less. That means their collisions happening would be very less, and so they would not be able to gain velocity, and they would be moving around with very, very small velocities, and so the temperature would also reduce at higher heights. So that's why on top of the mountains it's very cold, extremely cold, compared to at the bottom of the mountain, right? So is it clear?
Yes, clear.
Okay. All right. So with that, we can now move into the pressure in liquids, right? So before we do that, everybody understands the how do we deal with pressure in air, in any type of gaseous environment. What does it mean? How does pressure changes with the height in an gaseous environment, or you can say air or atmosphere?
Yes, I understand.
Okay, so assume that it's clear for everyone. Let me just see how much time do we have left.
2
2
minutes.
minutes. Okay, so should we start this topic? Yeah, I think we'll continue with pressure in liquids in the next class. And with that, we'll talk about Pascal's law. I think that's left, Pascal's law, and a little bit detail of hydraulics, right? How does an hydraulic brake in your car works, and so on. And with that, we'll finally just discuss manometer. Manometer is also an instrument just like a barometer, and manometer is also used to measure the pressure of a gas, really, right? So the gas can be anything. It can be, it can be any gas, not specifically atmospheric pressure, but you use the concept of atmospheric pressure in manometer to understand the pressure of the gas as well, right? So these are the things that we'll cover in the next class. I'll try my best to finish the chapter in the next class, and then we can start with thermodynamics, right? Temperatures and so on.
Teacher,
Yeah.
is pressure inversely proportional to volume?
Yes, it has to be inversely. So in a three-dimensional environment, area becomes volume, right? If area is a two-dimensional thing, and in a three dimensions you have volume, and so pressure would also be inversely proportional to that volume, right?